All right, now we're going to move on to springs. And Hooke's law is a concept here that is not very complicated, but it just fits in best here. You're actually going to do a lab or a mini lab in class that relates to Hooke's law. You're going to use it. Okay. So here we have a spring. We have a spring and a little scale here. And when I pull on the scale, it measures the newtons of force. And the spring here, like all springs, well, most springs, well, yeah, all springs. When you stretch it, it exerts a force on the thing that it's pulling against. And if you pull farther, it exerts a larger force. And if you pull even farther, it's a larger force than that. Okay, that's a characteristic of all springs. So the length that you pull it, the length that you stretch it, is related to the force that it produces. And the way we express that is called Hooke's law, and it is the spring force is equal to K times X. That's the way it's produced. It's related on your AP gouge, okay? So this is the force of the spring, force exerted by the spring in newtons. This is called the spring constant, and I'll get to that in just a moment. And then this is the distance of the stretch or the compression. So this is the stretch or compression. Because as you know, springs work when you compress them, like the springs in your car, as well as being pulled, like this one that I've got right here. They work either way, and Hooke's law applies to both. Okay, so as we observe, the farther I stretch this spring, the more force it exerts. So we could express that as so many newtons of force for however many meters of stretch. The more meters of stretch, the more newtons of force that it exerts. And the spring constant is the description of this spring, which tells us how strong it is. Basically, it is in newtons per meter. The spring constant is how many newtons of force you get for every meter of stretch in the spring itself. Okay, so for example, if I stretch this thing, let's go with 5 centimeters. Okay, that's probably a fairly reasonable amount here. It's roughly 0 right now. And if I pull it about 5 centimeters, well, it's okay, so it's a little bit more than that, but let's pretend. It goes up to 10 newtons, okay? Well, actually, that's about right. That's about 5 centimeters, okay? So we got 10 newtons of force when I stretch the thing 5 centimeters, in 5 centimeters. And we have to do this in newtons, in meters. So that is 0.05 meters. So this comes down to be, let's put this here, 10 newtons divided by 0.05 meters comes out to be 200. So the spring constant for this particular spring, with our approximations and measurements, is about 200 newtons per meter. Meaning that if I was somehow able to stretch this thing an entire meter, it would take 200 newtons of force to do it. Now, in reality, if I tried to pull this spring an entire meter, I would deform the spring. I would stretch it farther than it would be able to tolerate. And that's called the elastic limit. This is kind of trivia. You don't need to know this so much. But the elastic limit is how far a spring can go before it is permanently deformed, before it won't return to its original dimensions. Okay, and Hooke's law applies to springs until they reach their elastic limit if the spring constant is truly constant through its whole stretch. And it turns out that that's usually the case with most springs, even natural ones. Like if you take a tree branch and you flex it to make like a homemade bow and arrow or something like that, most springs actually follow Hooke's law pretty closely. It's kind of interesting. It looks like some sort of idealized thing, but it actually reflects reality pretty well. Okay, so this is Hooke's law. The force of the spring is equal to the spring constant times how far you stretch it. So the farther we stretch this spring, the more force it's going to produce. Now, another way to express Hooke's law is basically just kind of by the definition of the spring constant. K is equal to newtons per meter. That's what it comes down to. If we rearrange this, bring the meters over to this side, K is equal to newtons divided by meters. So just remembering what the spring constant is and represents helps you represent Hooke's law. And given information like this, you can say, okay, well, spring constant, 10 newtons divided by 0.05 meters, just like we did. That's all there is to it. And once you have the spring constant, then you can plug in any distance that you want and figure out how much force you'll get out of it. Or alternatively, if you need a particular force, you can figure out how far you need to stretch the spring to produce that force. Okay, so fairly straightforward thing. You have a couple homework problems where you get to practice that. That's the strange page. Let's see, it's 200 and yeah, you have some questions that are on page 244, and those are the ones that deal with Hooke's law and the spring constant. Okay, now what are we going to do with this? How does this relate to spring potential energy? And I see I used up some of my space here, but I think we'll still be able to fit it in here. So there's an equation for spring potential energy. And that is U because that's still potential energy, and they abbreviate it US, meaning spring potential energy, as opposed to gravitational potential energy. And it is equal to 1/2 K being the spring constant, X squared. So this is the spring potential energy, and it's going to be in joules. K is the spring constant in newtons per meter. And X is the distance of the stretch, which is going to be meters, and that's going to be quantity squared. Okay, meters quantity squared. Now, we have newtons per meter times meters squared. So if we're working out the units here, one of these meters goes away, one of these meters goes away. It leaves us with Newton meters, which you probably recognize as the unit of work or potential energy, joules. So this truly does produce joules. So for example, if we have our spring that we were just looking here with a spring constant of 200 Newton meters, suppose we do stretch it, say, 20 centimeters. We're going to stretch it 20 centimeters. Yeah, that's showing up on the screen. That's fine, which is equal to 0.2 meters. How many joules of potential energy are stored in the spring? Okay, so a spring actually does store energy, and when you release it, it snaps and it does work on whatever it runs into. So the potential energy actually is in the spring, and which is a straight plug and play. So this is going to be 1/2 times 200, because that's our spring constant in this case, times 0.2 meters, and that quantity is squared. And so we get 200 divided by 2 is 100 times 0.2 meters quantity squared, and we get 4 joules. 4 joules of potential energy in this spring. If I actually stretch it out 20 centimeters, I'm not sure I want to do that because I think I'll deform it, but if I did, it would store 4 joules of spring potential energy. That's all there is to it. Sometimes they will give you like the amount of energy stored in the spring and how far it's stretched and ask you to find K, or maybe they'll give you the amount of energy that you want to store and the spring constant, and you got to figure out how far you have to stretch it. Many ways to do this. Okay, so that's spring potential energy. What does that leave us with here? Let's go back to this one. And that brings us to thermal energy. We're wrapping it up here, getting close to the end. Okay, so thermal energy, as I said, this is where the energy goes in the bowling ball when it landed on the floor. And it went bang, and it shook the floor, and it stopped. and it had no potential energy because it was as low as it could go, and it had no kinetic energy because it wasn't moving anymore. Where did the energy go if energy is conserved? Well, what it did is it heated up the ground. That's what it did. And to some degree, it also heated up the air a little bit. We heard that bang when it hit the ground because it shook all of the air molecules in the room. It sent out a pressure wave and made the air molecules move. And when that wave got to our ears, it shook our eardrums and transferred some energy to our eardrums. But if the sound just bounces around the room, eventually it's going to just make all of the air molecules in the room shake a little bit more. And as you know, things get warm because the atoms and molecules in them move, are shaking more. So by shaking the air molecules in the room, we are heating up the air in the room, and that's where the energy went. Some of the energy went. Most of the energy went to hitting the floor and heating up the floor because, again, it shakes the floor. It makes the molecules in the linoleum floor vibrate and shake, and it makes it physically warmer. If any of you have ever split wood with a sledgehammer and a wedge, you know that if you hit the wedge a whole bunch of times with the hammer, the wedge starts to get hot because that kinetic energy of the hammerhead hitting the wedge heats it up. It makes those molecules shake. It gets warm. So the energy takes the form of thermal energy in that case, in the wedge or in the floor when I drop the bowling ball on the floor. Okay, so whenever you do a problem and it looks like energy just vanished, it went to thermal energy. And they'll say, well, how much thermal energy is produced when a block slides down a ramp? Well, the block wasn't moving when it was up high, and it's not moving anymore when it gets to the bottom, so there's no kinetic energy. But clearly some potential energy disappeared because it went from a high position to a low position. Where did it go? Well, it went into heating up the ramp as it slid down the ramp, or it went into heating up a stop block on the bottom when it ran into it, just like the bowling ball hitting the floor. So when you're doing a problem and energy seems to disappear from the system, it went to thermal energy. That's a direct application of this concept of conservation of energy. Okay, the energy has to go somewhere, and if it's not potential anymore, and if it's not if it's not kinetic energy anymore, and it hasn't gone into stretching a spring or something like that, it's thermal. Now, occasionally it is possible to calculate thermal energy directly, particularly when there's friction. Okay, so if we're dragging a block across the floor, there's a force of friction holding that block back. And all the time that we're dragging it along, we're working against that force of friction. So if we know the force of friction, and you guys know how to do that because you've used the friction equation before, and if you've forgotten, it's on the AP gouge, and you can find it in your notes or in the book. But once you calculate the force of friction, well, the entire distance that you dragged that block across the floor, well, that's the distance that you were working against the friction. So you were literally working against friction. You're transferring energy to that friction. And what does the friction do? Well, friction heats things up. You rub your hands together, there's friction, it makes your hands warmer. So when you drag a block across the floor, it's heating up the floor. And that's the thermal energy that goes into the floor, is the work you did against friction. Okay, now, if you're dragging a block like up a ramp, well, now some of that energy is going into potential energy. So you would look at the work you did against the frictional force and the distance up the ramp, and then you'd calculate, well, how much of that energy actually went into potential energy. And usually it's not going to quite add up. You did more work than there is in potential energy. Well, the remaining missing energy was thermal energy. It heated up the system. Okay, that should be enough to get you going. This was kind of a long one, but like I say, grab bag of lots of interesting things. So thank you for your time, and we will see you next time.